Uh, so, hi everyone. My name is Elviro, and I come from Italy, and I love monads. Okay. I hope most of the people here love monads, or at least tolerate them. And what I'm going to talk about is basically some useful things, very simple useful things that you can do if you basically let yourself go with monads. You start seeing monads everywhere, you start using them. Just to get everyone on the same page, I'm going to recap a little bit about the things that are important, I think, about monads. We all like function composition. So if I have a function from A to B and a function from B to C, I can always compose them in a function from A to C, and I can go all the way down. The problem arises when I have a situation like this, in which my functions are not just simple function from A to B, B to C, but are functions from, for example, A to something that is related to B, but we are adding some stuff to it. We are adding some semantics, some behavior, and of course, this is not trivially composable, because the types don't match. We don't have B on the right side. And so it might be hard to understand what these plus signs do. But it turns out that if these M's here are monads, okay, we can actually implement a generic way to, to implement these plus signs. For example, if these functions are a function from something to an optional something else, A to optional B, B to optional C, we know that we can do this in Swift natively. Also, if M is a monad there, we also get a lot of other things for free. We have this function for free, a function that wraps the types inside the monad. So the monad acts like a container, a box that contains the type A. We also have this for free, because monads are also functors. So if we have a function that transforms the contain type, we can always get a function that transforms the entire container. And we usually do this in Swift like this. So we have an instance of the container, and we call map on the container with the function A to B, and we end up with a different kind of container. Now, I am using the word container a lot because I like the intuition of a container for monads and functors. Now, I read some criticism about this, but I never read very compelling arguments against the container abstraction, so if you don't agree, we can talk about it later. But basically, what I mean is that every instance in which I have a monad that's called A and the generic type is B, I'm going to say A contains B. Now, actually, there are not many monads in current use. There's just a bunch of them. I use the deferred monads, is the second from the top. It's sometimes the monad is called future. The monads that I'm going to talk about in this talk are these three, because these are the monads that are relevant for my example. Now, I assume that everyone is familiar with the result type. This is the Schrödinger monad, because this is a box that can contain a value or an error, exclusive OR. So we don't know what's inside the result until we open it. If there is a value, there is no error, and of course, if we have an error, there is no value. But until we open it, we can treat it as both of the thing. The deferred type is a container that it's expected to contain a value of type A, for example, but when we instantiate it, there is no value inside. So something happens, some computation. We expect the value of type A to be inside the defer at a certain point in time. Okay. So what we can do with this deferred is that we can register a bunch of callbacks, functions that will be called when the A is there, and so when the A is actually there, the deferred will call all the callbacks. And that's it. We don't know when the A will be inside. Actually, the A could be inside from the very beginning. The deferred monad is something that we can use when we want to represent an asynchronous computation. Okay. So if someone is familiar with observables more than this, I don't know how it's possible, but the defer is basically a single observable, just one single value. Of course, we can flat map the deferred, we can initialize the deferred. This is with a value, the defer is a full-fledged, okay, monads. An interesting use case could be this. If we could have this function, okay, get resource. We take a model, and we end up with a resource, but a deferred resource, because maybe we don't have it immediately. We have to do something in background, some calculation, some computation to get the resource. And this is the classic use case for an HTTP request. That's the generic function A deferred B. A is the model, and B is the resource. Flat mapping and a deferred basically means that if I have a second function that takes as model the previous resource, I can just chain these two things. I can concatenate the functions, and if these are HTTP requests, for example, when the first finishes, the second will start. Last but not least, the writer. This is my favorite monad. The writer is a box that contains two things. One is the main thing, and the main value, the generic parameter that we are talking about. And the second value is just a secondary thing, is some additional information. So when we transform this, we might transform this with a function that transforms the A into a B, but there's also some additional information there, an L2. And what we end up with is a container with B, and basically both the L's, both the additional information that are composed somehow, okay? And this goes on and on. So writer can be used when we want to represent computations in which we want to carry over some additional thing, some additional information, okay? One classic use case, but this is not the only one, is logging. Instead of logging to the console, we could add this log as the additional type, the writer. The log is a monoid, which means basically that the composition of two logs is associative, and there must also be an empty log, a neutral empty value. And the reason for this is that we need to be able to create a writer with just the value of type A. So there has to be a log that can be created out of thin air and that is empty, basically ignored. Now, let's see a use case for our HTTP request. For example, we would like to add some connection info. Okay, the HTTP request is actually a complex process, and when the request, when we have the resource, so the request completes, basically for logging purposes, we could accumulate, we would want to accumulate some connection info. For example, the original request, the headers, the response of the server, I don't know, the HTTP code, the headers, everybody that's ever worked with backend people in the same team probably wants to do this, because sometimes things don't work and you don't really know if they change something in the backend or if it's your fault. So you want to be able to debug your HTTP requests. Now, how can we add this connection info here? We could add it to the resource type, but we already have some type that represents the idea of carrying over some information, and is the writer type. So we would like to combine the two things, a deferred with a writer. And the way to do this, okay, is put the writer inside the deferred. Instead of having directly the resource there, we could have the deferred of a writer. And another thing, of course, could be a connection error. Again, we could encode the failure case inside our resource. But again, it's not really composable. A resource should be a very pure thing. So we could add the idea of a connection error here, and we talk about how to add the possibility of an error to a computation, and it's with the result type. So we can add a result inside the writer, inside the deferred. So this is the type we end up with, okay? We have a deferred of a writer of a result, and the result as the secondary type, okay, is the connection error. And the secondary type of the writer is a connection info. This is fun. But the problem arises when we want to map or flat map this, because one thing, interesting thing about monads, of course, is the fact that we can easily transform them, combine them, compose them with functions that give us other monads, etc. But if we want to map this, basically we should pass to the map function avrider, or to the flat function avrider that returns the third of avrider, etc. Really, we would really like to act directly on the resource here. So just go inside this chain of monads, this tower of monads, actually, and operate directly on the resource. To put it generically, we are talking about something like this. If we have a monad of A and this transformation function, we would like to encode the plus sign. Okay, so we get a monad of B. And of course, the same thing with the flat map. Now, I'm going to show a few graphs and very few code. Graphs like this, in which I am representing my types with these circles with the letters inside. And when I put a circle on top of another, it means that the first one contains the second one. This is what we want to do. We have a container, A, that contains a value type B, and we want to transform the entire container. The container is the same in our transformation, but the value inside changes. So if we have this function here, a function from B1 to B2, the blue line is something that we have, and A is a functor. If it's a monad, it's also a functor. Means that we have these green arrows here. Green arrows are things that we get for free, just for the semantics of the type. So we can do this. We can get the black arrow by composing the other arrows. Okay. If we have a tower that is a little bit deeper, we might end up with this case in which we have the transformation function from C1 to C2. But we really want to transform the whole thing. Now, if A is a functor, this is the situation. We need a function from B to B. It's red, so something that we do not have, but we need. But of course, if B is also a functor, we have this set up here. So actually, the black arrow there says to me, you actually have this function. You don't know, but you have it. So I represented that with the dotted line. Okay, something that we don't have right away, but we have it from the context. And this is what we end up with. This is not just a map. It's like a deeper map. And of course, we can go deeper and deeper. The only thing that we require is that every container here is a functor. Now, if we want to represent these transformations as methods on A, because this is the way I like it, because this is what I have. I have an instance of A, and there's something inside. I like to use methods to transform A, and I call this mapping deeper map operation map T. Map T, double T, triple T, at any level, basically. Now, flat map. Flat map means if I have this function here, okay, I have a function from B1 to the other container. If A is a monad, I get this arrow for free. So I can actually transform the whole thing. The monad basically allows me to change context. The initial context is A that contains B1. The final context is A that contains B2. Now, if the situation is this, the flat map is not going to be enough, because flat map really to work, it really needs this function here. How can I get that function, the red arrow? Well, if somehow I add this arrow here, and a function from B to C1, I could actually, of course, construct the whole thing. I could go from A to B, C1, and again to A. But I would need a function from B to C1. What this means, basically, is that I need to be able to explore the type B. B contains C1. I need to be able to go inside B in some way and extract the C1. Either is this or something like this. If there is no C1 into B, I might be able to actually rebuild the other monad tower, container tower, by just ignoring the function from C1 to A, because B is a container, there might be a C1, but maybe there is something else. If B is a result, for example, there might be C1 or there might be an error. For doing this, I need to be able to reconstruct A just from a B. And if A is a monad, of course, I can do this. So this is another option, another possibility for this situation. This seems like a map, but it's not. I am actually reconstructing the other tower because I know that inside B there is really no C1. It should be, but it's not there. So I need to be able to explore these containers and extract the values. If I can do this, I can add methods on A, and of course I call them flatMapT, flatMapDoubleT, etc. Of course, I can go even deeper. If I'm able to extract a value, the value from B, and get a C, I have this setup here. I need the red arrow, but again, if I can do the same thing for C, so if also C is a container from which I can extract the value, I can explore and extract the value, I can do something like this and end up with this situation. So these are the two, an overview of the two transformations here. For the left transformations, I just need that A and B and C are functors. For the right part, I need that A is a monad, so I need to be able to flat map it. And actually, I need B and C to be special kind of containers. Now, we are going to see what I mean with this special kind of container thing. Let's observe first that in Swift, we cannot generically represent a functor or a monad because the type system doesn't allow us to do that. It's not powerful enough. But what we can do, okay, is we can use, we can represent our monads with protocols, and then we can add methods to protocols with constrained extensions, so extensions in which we constrain the parameters. What I mean is that even if I have actually concrete type for deferred, rider, and result, I really want to define protocols for these types. And basically, what I'm going to do is I'm going to add the map and flat map functions to the protocols. Of course, these functions return the concrete type, because in Swift I need to do this. I need to return a concrete type from a function. And actually, here I prefer to express my monad with a joined function. It is the one in the middle. If I have a monad inside another monad and the monads are the same, I can flatten them into a single one. And the flat map is defined in terms of map and joined. But this is like the sequence protocol in Swift. A sequence, for example, has a default implementation for a map that returns an array. Okay, I can override that implementation in my concrete type, but the default implementation has to return an array. It doesn't return a sequence, okay? It returns actually an array. Now that I have protocols, I can write extensions to these protocols and constrain them. For example, I could write an extension of the defer type when the element type is a rider type. And I can implement mapT. Once I implemented mapT, I can implement mapDoubleT when I have my element type is a rider type, and the element type of the element type is a result type. Now, this is crazy, of course, because if I had to write this by hand, this would be extremely laborious and error-prone. But the structure inside is always the same, because I am double mapping at the beginning, and then I am changing the first map to mapT, mapDoubleT, etc. So this seems the perfect match for code generation. And as many of you probably, I use sorcery to generate code when the structure of the code is always the same, and only a few things changes, the types. What sorcery does is you provide sorcery with templates. I use the stencil templating language, and sorcery will generate the source files from those templates. Now, stencil templates are extremely hard to read. I really don't, I mean, what I just wanted to show you is the fact that this code here is everything that I need to generate my mapT and mapDoubleT methods for basically any possible type that I annotate with map. I have all these protocols. I annotate them with map. I say, this, I can map this. I can say to sorcery, I can map this. And sorcery just generates the entirety of the entire code that I need. And this actually is enough for map. You can use macros. The first two blocks at the top are macros in sorcery to make the thing a little bit more readable, but it's extremely hard to read, so it's not useful for a slide. Okay. What about flat map? Now, as I said, it's not just I need to generically express the idea of a monad, so the fact that I can flat map something. I also need to explore, okay, this container. This container must be somehow traversable, okay? I must be able to explore them and understand if there's a value inside, if there is no value. So of course, probably I'm not going to be able to use just one template for sorcery. I am going to need one template for each kind of container. And I was able to do this with these 6 monads. The grayed out one, I wasn't able to do that. But I'm still, I'm still researching this, I'm still exploring this. I used this for I started using this a couple of years ago for my main use case, that was the HTTP request, but I'm, exploring the thing. By that I mean that for generating all the code that I need for flatmap T, double T, etc., I need to write 6 templates, one for each and every type. There are actually additional requests. For example, for the template of an array, I need that every type that contains the array must be also an applicative. But the point is, every template will be a little different. Okay. For example, this is for the writer type. The bold code is specific to the writer. Everything else, okay, it's not specific for the writer really. It's basically related to the fact that this the types, the container types, can be mapped and can be joined, so can be flat map. Now the final result, when you can put all this code in a library, and you probably want to do this because you are going to generate files with thousands of lines, and they take a while, not that while, like 10 seconds to build, but in the end, if you have all this in place, when you have one of these containers, the Xcode autocomplete will look like this. You have X, that is this crazy container. You start writing up, and you get all the options laid out, and you will be able basically to use the one that suits your needs. It really depends on the type, okay, on the type of transformation that you want to apply. For example, sometimes I want to change my result that's inside, because even if I don't get an error in the HTTP request, I probably want to end up with an error because, I don't know, the server output is not the one I was expecting. So to recap, each monad encapsulates specific logic and semantics. That's why monads might be useful. That's why when you have some computations, you might want to use some of them, because you recognize that the monad actually already encapsulates the thing that you're trying to do. But the best thing about monads is that you can combine more monads, okay, for more powerful behavior. Now, for chained mapping, so if we want to write map function that go deeper, we really just need the containers to be functors. But for flat mapping, well, we need the chain top to be a monad. Every other container must be a specific kind of container, an explorable container, and we need to write a template for each and every one of them. Now, we cannot represent generically functor of monads, okay, or monads, but we can write protocol extensions that are constrained to some specific type. And then we end up using code generation to generate all the code that has all the same structure. As I said, a template for each specific container at the end of the chain. And that's all I had. Thanks. Do you want to take questions? Yeah, of course. Yeah.
So you mentioned that the first sort of like concrete use case for this pattern is in sort of instrumenting your HTTP requests.
Yep.
I was curious if you had another sort of place where you found this pattern to be super useful, just like applied into your code base.
Yeah. For example, I use a writer to represent my user session, but the main value inside the writer, the user session means that the secondary type, okay, of the writer, the accumulated, okay, result, the accumulated log, okay, of the typer, the writer, is a struct that contains some user session specific things. For example, the log, the user, the JVT token of the request, etc. These things are going to be updated during a series of transformations. For example, after every HTTP request, I update the JVT token inside. But inside the main type of the writer could be anything, because I use that writer because I want to represent, I need a value to make my requests. The value has to be contained inside this user session, but this value could be anything. So for example, I end up using results inside, or optionals inside, or even arrays. Okay, this is interesting because you can do this even if at the bottom of your chain is an array, okay, and you are going to, this means that if you have a bunch of things and you want to transform them all together, you can traverse the array and transform the whole thing. So this might be an application. I think, Brandon.
Do you have the code gen for composing applicatives?
The code gen for composing applicatives in a lib. Okay, I think what you mean is if those types are applicatives, do I have the code gen for the apply function? Yes. In this library here, I just put all these things, and there are, I think, 10 templates, sorcery templates that do all sorts of things. And yes, there is also the apply templates that generates applicatives. What you need to do is you need to tell sorcery that this thing can be an applicative. And you actually can deduce the thing, because actually if it's a functor and as an apply function, okay, you can generate all the applicatives. The way I do this really is in terms of the zip function. I have I define the zip function for my monads. The zip function means that if I have two monads of the same type, I can create a monad of the tuple, and you can deduce apply from that. Because if you have a container with a value and a container with a function, and you are able to zip these two containers into a container with both the value and the function, you just apply the function. And then I deduce the apply method from this. So yes, there might be different, I could also go the other way around, okay? I could define zip in terms of flat map, but for some types you don't want to do this, because for example, if you do it for the deferred, and define it in terms of flat map, the zipped values inside the deferred are going to be got in sequence, and probably you want to get them in parallel. So we can just define the zip function, and you tell sorcery, you know, this type has a zip function, just generate the applicative definition.
So traditionally, when people have the user session in their app, they unfortunately use global state, right?
Mm-hmm.
But with the writer, you're able to get rid of that part of your global state. What I want to know is how much of your of the things that traditionally would live in some sort of global state have you been able to push into your monad transformer stacks?
Okay. I think almost everything, because the only thing that is in my current app is at the global level is the fact that I have basically an entire view model for my application that contains the entire structure of all the views, and this is stored into a class, so into a reference type. But, and somehow, and sometimes I have to inject this thing in functions, so I just write functions that get these things in. But I think, I don't know. The point is not everything is a monoid, okay? So for actually doing this in the writer way, you need to have the associated, the secondary value must be a monoid. But for example, you can actually just create pairs, okay? and define them as bifunctors. So they will be mapped with two functions. So I think you can push yourself as long as you want, as much as you want. I like to push this thing as hard as possible. And sometimes I end up with things that are a little silly, okay? But they are silly just because Swift maybe is not the perfect match for these kind of things. But it's worth trying it, okay? It's worth trying to avoid as much global state as you can. Then when you end up with this absurd, when you realize that maybe you need an absurd semantic tower to represent things without a global state, you say, you know what? I will do this a little differently. But it's worth trying.
Let's leave it at that.
What?
Let's leave it at that.
Okay.